Good morning, good afternoon, good evening. My name is Dan Marius Dobra. I am from Romania and I am from Gheorghe Saki Technical University of Iași, Faculty of Electronics, Telecommunication and Information Technology. In this presentation, I will show two practical applications based on the real-time NuttX operating system. Both applications were developed in the frame of the NXP Hover Game Challenge, a competition in which I participated in all 3 years of occurrence. A competition in which I took first place twice and second place once. The applications aim: the first one to detect people in the area with forest fire, and the second one is to detect and classify diseases in the vineyard. Both applications are based on an UAV system that was especially developed for each of them. As you know, NuttX is a scalable, small footprint, efficient, very stable and open source real-time operating system. And it is also, from my point of view, the base for running PX4 autopilot on a flight management board. I interacted with the NuttX operating system at many levels, as you will see in my presentation, and it is important to have a best understanding of it in order to achieve good results. One of the most disturbing problems in fire is the human death toll. As a direct result, one of the most significant challenges the rescue and search team face during a fire in the wilderness is the actual search for survivors and victims. So, this project aimed to develop a real-time UAV system capable of detecting humans in disastrous conditions like fires. The solution is based on an autonomous UAV that is able to both detect humans and send warnings promptly to a control center. The UAV system will carry a pre-programmed flight mission by following a planned path above the interesting zone, and at the end of the mission it will return to the landing point. These functions are embedded in the PX4 autopilot. The UAV system was built based on the Hover Game Drone Kit, which is a professional development kit produced by NXP Semiconductors. This kit contains all the required components needed to build a quadcopter, such as frame, motors, flight management unit or power distribution board. The human detection function was implemented using a Raspberry Pi as a companion computer. Also, an FPV system was used to check the detection made by the intelligence system independently. The Hover Game drone can fly autonomously, but based on a radio control link, a ground control operator can take control of the drone, switching from the autonomous mode to the manual mode. By using a telemetry connection, which is a main link with the ground station, it is possible to configure the flight path, supervise and change settings and parameters on the flight management unit, and in this mode to check the status of the Hover Game's quadcopter while it is in air, but most of all, the human detection from the Raspberry Pi are sent to the ground station based on this link. Communication between the flight management unit and the companion computer was done by using an I2C protocol. In the case of the human detection system, nothing is special or unusual. The HAR cascade provided by the OpenCV and a linear SVM classifier were used to perform human detection in the video streams. Of course, any other type of detection system can be used here. But there was a problem. In a real situation, human detection took between 2.4 and 2.9 seconds, and this detection time was unacceptable. To solve this problem, a multi-thread approach was employed, in which the 3 different recognition threads were running on the 3 distinct cores of the Raspberry Pi system in parallel. So, the main idea is to start this thread using a timer, but each thread was delayed by a third of the detection time. The detection speed improved in this mode, and in this mode I got around 1 frame per second. Right now, we have the detection, and you must send these results to the ground control station. To achieve this goal, a special app running on the NuttX operating system was developed as an independent module able to get the detection result through the I2C bus from the Raspberry Pi and communicate with the PX4 based on Vineyard messaging. Based on these messages, the information was sent to the telemetry link to the ground control station. So, my app creates a background task based on this function, and this new background task runs independently from the parent. In the background task, I created and initialized several objects, such as a named semaphore and a timer. This was a point where I start to fall in love with the NuttX operating system. Due to compliance with the POSIX standard, all the interfaces for these components are identical to the one found in the Linux distributions. So, to develop this app, I first created and configured a timer. Based on this configuration, the kernel will send a signal each time the timer expires. In the second section, the timer expiration values are set and the timer is armed. In the last step, the signals and my functions association is made based on the SIG action system call. In this function, the human detection information is obtained through the I2C bus and sent to the PX4 autopilot based on the Vineyard messages. Of course, in the end, the PX4 autopilot sends this information to the ground station based on the Mavlink protocol. In conclusion, it is very easy and straightforward to develop code in the NuttX operating system, and all the knowledge acquired in the frame of the Linux can be used in the NuttX without any difficulties. So, the second application. The main idea is that there is a growing need for food worldwide, and this need requires the development of high performances, high productivity, and sustainable agriculture, which implies the introduction of new technology into each stage of plant development. However, many elements affect crop development. One of the most important is a different type of diseases. In this project, I had developed an intelligent system to assess the healthiness of the vines based on the characteristics resulting from the analysis of the vine leaves, like texture, shape, or color. The intelligent system presented here is able to detect two different diseases. The first one is blister mite, which is generated by a mite species infecting grape leaves. This disease is also a vector for other viruses that affect vines. The treatment for this disease should be applied when the first mite appear. If they are allowed to develop, they will do so quickly, mainly because this mite has between 5 to 7 generations in a year. The second detected disease is grapevine leaf roll. This disease is one of the most important grapevine viral diseases affecting vine grape worldwide. The main problem with the grapevine leaf roll diseases is that there are no way to cure an infected vine and is no chemical control for grapevine leaf roll diseases. Therefore, the only solution is to remove and destroy the virus-infected vines. So, as a direct conclusion, the field surveys and the detection of the grapevine leaf roll diseases are the only valid approach used up to this moment. The grapevine leaf roll diseases is considered one of the most economically destructive grapevine virus diseases. There are many estimates of the economic cost worldwide. Some estimate loss ranges from $30,000 to $226,000 per hectare, or other approximation starts from $25,000 up to $40,000 per hectare, or up to 77% revenue decline. So, as a direct conclusion, this intelligent system is important because a timely diagnostic and accurate identification of grape leaf diseases are decisive for controlling diseases spread and ensuring the grape healthy development. Moreover, the early detection of diseases will determine the use of pesticide only when necessary, with a positive impact on the environment. The intelligent detection system is supported by an IMX8 Plus development board, known under the name of NavQ Plus, carried over the entire Vineyard by our NXP Hover Games drone, a drone that was presented before. The development board also has a neural processing unit, on which the deep neural network is executed in real time. At the level of the IMX8M Plus, the functionalities were implemented using the support of ROS2 operating system. Additionally, a 0MQ client application and a 0MQ server was used for debugging the developed application in real time. The system incorporates a depth sensor to guide the drone through the rows of vines. For vines planted industrially with mechanized soil maintenance, there is a distance between 2.2 up to 2.5 meters between rows, so we have plenty of space to fly. The Google Coral camera was used for plant anomaly detection. The depth sensor has also an RGB camera that could be used instead of the Google Coral camera. Still, the functionality were implemented on the two cameras to ensure that the data stream could be received without any lags. Next, mainly because maintaining a constant altitude through the GPS and the barometer sensor is not very accurate, I also included a LiDAR light type sensor in the system. The component that implements the software part of the UAV drone were developed as a single ROS2 package having 4 nodes. All communication and synchronize between nodes were done through topics. The detection system is based on the TensorFlow Lite model and runs on the health plant node. The detection system starts when the UAV drone is set in off-board mode. The node takes note for this fact from the flight control node through the flight off-board topic, and in this mode the detection process starts. The health plant node published 2 topics related to the detection process: detect vitis and detect leaf roll. These 2 topics post the area of leaves for each class detected. This publication of the affected leaf area can be used to create a real-time map of the extent of crop damage. The flight control node is connected to the PX4 autopilot, being able to control the UAV based on the velocity and position modes. It also able to know the status of the drone at each moment. This node can arm, disarm, take off, land the drone accordingly with the necessities resulting from the off-board control. Each of the following node, video publisher, flight control, health plant node, has a specific topic used to publish images from the debugging process. The video broadcast node can subscribe to a specific image topic and stream the images to the 0MQ video server through the 0MQ streaming protocol based on the Wi-Fi link. Mainly because in this project I want to detect only 2 types of leaves, and because these leaves do not belong to the categories in which classically deep learning networks were trained, I use the transfer learning paradigm. So I use MobileNet deep neural network that is widely used for image detection and recognition. This neural network has already trained layers able to identify different features like outlines, curve, edge, etc. Training these layers require a lot of training data and also required a lot of training time. Using all of this embedded knowledge, I only retrain the last layer, which will be replaced with a new one with output for detecting elements probabilities and outputs pointing to a specific area in the input frame. So, in order to train the last layer, a new training database was created, having images for the two classes. 80% of the database was used for training and 20% for testing. 4. The image annotation, model selection according to the desired accuracy, model training, model optimization for efficient NPU execution, and model validation. I used the EAQ environment. Following the training process, the detection performances was a little bit more than 86%. Okay, but keep in mind this project was a proof of concept. Thus, I was able to prove the functionality of this approach, and of course it can be applied in the same ways to assess the health of fruit trees, maize, rice, or any other plant based on the state of the leaves. Right now I am working to increase the classification performances. From the point of view of the NuttX operating system, I had less interaction in this project with this operating system. My application was developed entirely on the companion computer and communicate with the PX4 autopilot through the micro RTPS bridge. For example, I interacted with the NuttX when I built the autopilot. Here you can see menu config tool. Of course, here is a graphical user interface variant used to modify the PX4 board configuration, adding removing modules, drivers, and other features like NuttX components. In addition, the client component of the micro RTPS bridge was executed at the boot time of the flight management unit based on the NuttX OS feature. Moreover, I extensively use the NuttX integrated shell interpreter to launch different component drivers or to check the state of the system, like CPU and memory usage, the state of the GPU, the state of the GPS, to test the motors, scan for I2C devices, to list topics, to list the content of the topic, to check the state of the Mavlink connection, or to erase the flash memory. In conclusion, the NuttX operating system is an essential component of any PX4 UAV. In my case, a hover game drone produced by NXP company. And, most important, a deep understanding of this operating system will help you build a UAV system that is as safe, effective, and reliable as possible. Thank you very much.